about Venus? Okay, so welcome to the Venus video. We're going to start by looking at the semi-major axis, very common variable that we've been looking at for the past episodes in our series, planets in our universe. So we're going to start by looking at the changes that we made. Instead of having mu and theta as the aphelion and the perihelion, we've used A and P. So as you can see in the calculation, Z is the semi-major axis according to the note. That note in white, which says this diagram shows Venus longest and shortest distances from the Sun. So you see A is the longest distance, P is the shortest distance, as you can see with the yellow and the blue brackets. So the semi-major axis is equal to the sum of the aphelion and the perihelion divided by 2, basically like the average. And what we get is 0.7233, which is approximately equal to 0.723 astronomical units, correct to 3 significant figures. So that's the semi-major axis in terms of astronomical units, in correct to 3 significant figures. Okay, so now we're looking at the orbital period of Venus. But first of all, we need to look at Kepler's third law, which states the squares of the orbital periods of the planets are directly proportional to the cubes of the semi-major axis of their orbits, as shown in the two examples there. For the orbital period and the semi-major axis, we're trying to derive the expressions for the two variables, and we see that it's t squared over r cubed. That's basically the expression that is explained in that law. Then the expressions for Venus orbital period and Venus semi-major axis are, as you can see, derived there. But if you don't understand, I would encourage you to watch the Mercury and the Make videos or episodes of the planet series. The explanation was clear there. I tried to explain everything clearly, so you can watch that if you don't understand. So now let's move on to the calculation of the orbital period. Okay, so the Kepler's third law is also written there. If you have forgotten, you can just refer to it there. You don't need to go back to the previous slide. So as you can see with the calculations there, we are going to calculate the orbital period, but we're going to use the SI units, the standard international units. The standard international part is French, that's why it's SI. So we use those SI units, the kgs, meters, seconds, and the like, the candela, and all those other units that are standard. Okay, so with our variables here, we have t, which is the period, z, which is the semi-major axis, g, which is the gravitational constant, and capital letter M, which is the mass of the Sun. That's very important because it's orbiting the Sun. So the semi-major axis is the separation between the Sun and Venus, which is orbiting the Sun, and Venus is the second planet from the Sun. So it has a shorter orbital path compared to the other parts of the other orbits of the other planets. Okay, so let's move on. We have t is equal to pi multiplied by the square root of z cubed, which is 1.08208 times 10 to the power 11 cubed, divided by 6.74 times 10 to the power negative 11. That's the gravitational constant. And then multiplied by that 1.99 times 10 to the power 30, which is the mass of the Sun. That's the denominator, that product of the two. And then we get our answer is 19,406,592.39. That's in second, but we need to convert it to days so that we have a smaller number to deal with, a smaller magnitude. Which means we divide by 86,400 seconds. That's 60 seconds times 60 minutes times 24 hours. That will give you 86,400 seconds. So we divide those seconds into that seconds, and then we get that value, which is approximately equal to 225 days. So it takes Venus takes 225 days, Earth days, to orbit the sun, to go around the sun in that orbit. But remember, when you looked at eccentricity, there's a funny shape that is produced by each and every orbit, or each and every ellipse, because of the gravity and all those attractions and the like of the bodies in the solar system and in the universe in general. So they might not be perfectly circular in terms of their shape, the ellipse, or the path in which Venus will be moving around the sun. So if you don't get it, you might need to watch the previous episode, which is the episode on planet Mercury, the first planet, which is the planet which is closest to the sun in the solar system. So you might need to watch the eccentricity part of that video to understand what I'm talking about in terms of the shape of the path, or the eccentricity of the ellipse. Okay, now let's move on to the relationship between orbital periods of the planets and their respective semi-major axis. So we calculate the semi-major axis and the orbital period for Venus. Now let's compare it to the others, the other planets. So we have the vertical axis, which is the orbital period in Earth years, which is dependent on the semi-major axis, which is the average distance from the sun. So as you can see with the points that have been plotted, we have Mercury, which is the lowest, followed by Venus, then Earth, then Mars, going forward until we reach Neptune at the top there. So which means Mercury and Venus have a shorter distance from the sun, therefore they have a shorter orbital period. They go around the sun in the shortest time possible compared to the other planets. But with Neptune, because it's far away from the sun, it takes a longer time to go around the sun, to circumambulate the sun, compared to Venus and Mercury and the like. So as the distance increases, the semi-major axis, as it increases, the orbital period also increases, which means there is a positive correlation due to the direct proportionality of the two variables. Remember Kepler's third law, that the cube of the separation of the masses is directly proportional to the square of the period. In this case, we see that being portrayed in this graph. So there's a positive correlation showing a direct proportionality of the two variables, the orbital period and the semi-major axis. So I hope you get the idea that Venus has a smaller orbit, and it is one of the shortest distances from the sun, the second shortest distance from the sun compared to the other 8 planets. But it also has a shorter period, which means it also has a shorter period, except for with comparison to Mercury. Mercury is the shortest, then followed by Venus, but the other planets have longer orbital periods. They take long to go around the sun compared to Venus and Mercury. So I hope you understand that. I hope I've explained it clearly with the graph. The graph shows it quite well. So as aforementioned, eccentricity was explained in the previous episode, which is the episode on Mercury. So you might need to watch that for you to understand what's happening here. But basically, if we read that note, we might get an idea, which says eccentricity is the measure of the extent or degree of deviation of a body's orbit from its circularity, or the degree of losing its shape of a perfect circle. Don't worry about that diagram that you see. The deviation is greater than the actual deviation. If you look at the orbit of Venus, of Venus, it's close to a circular shape. It's not that close to an oval shape. Where was I? Okay, that's creating an ellipse. The eccentricity increases with an increase in the oval shape of an orbit. So it's how much it loses its circularity and how much of an oval shape is being created by the path. When eccentricity is equal to 0, the orbit will be a perfect circle, and that is proved by that equation that you see here. For it to be 0, it means that the aphelion over the perihelion has to be equal to 1. So 1 plus 1 will be 2, which means 2 over 2 is equal to 1. Then that 1 outside the brackets there minus the 1 that's in the brackets will then give you 0, which means the eccentricity is 0. So make sure that you understand what the equation, or rather what the expression is trying to tell, and related to that explanation and the definition of eccentricity. Okay, so let's look at the calculation right now. So our eccentricity is represented by the Greek letter epsilon, and epsilon is equal to 1 minus 2 being the numerator over the aphelion over the perihelion plus 1. And that aphelion, the perihelion, we are using astronomical units. We can use the one the metric unit, the metric system units, but here we are just using the astronomical units. So in astronomical units, we have that fraction, then plus 1 for the denominator, and then our answer will be 0.006774505. Yeah, that number, which is approximately equal to 0.00677 to correct to 3 significant figures. So that's our eccentricity for Venus. So as you can see, it's very much close to 0, which means that the eccentricity or rather the shape of the ellipse of Venus is supposed to be close to a circular shape, not that oval shape that you see on that diagram. That was a mistake, but hope you can understand. For that diagram, I think it will be probably close to 0.4, between 0.4 and 0.8. Rather, the eccentricity will be between 0.4 and 0.8. But here we have 0.006, which means it's very much less than 0.1, which means it's very close to circular shape. But let's just continue and learn more about Venus in the next slides, and hope you will benefit and enjoy from the series. Maybe you can just comment down below what you understand and what you like about this planet, or what you have learned about this planet that fascinated you. As for me, I think I'm done. Let's enjoy the rest of the video as we learn more about Venus. Till we meet again. Cheers. More on Venus. The Venetian environment.